All right. So Newton's second law. We talk about Newton's first law. Newton's second law actually starts off talking about proportionalities. Newton's first law was all about tendencies. But Newton's second law starts talking about proportionalities. What we say with the proportionality is that the acceleration of an object is directly proportional to the force. And I want to just think for a second about what that means. I like to think by doing it with a picture. And you can fit this picture up into your margin, but just for clarity, under the camera, I'm going to do it on a piece of Post-it note. If I have an object like this one, and I have another object, same size, and I have another object, same size, and somebody comes along and says, hey, I'd like to apply a force to that first object. I'm thinking I'm going to apply a little force. And somebody comes along to the second object and said, hey, I'd like to apply a bigger force. And we come to a third object. We say, hey, I'd like to apply an enormous force to that object. I want to do a little thought experiment on this one. Now, the force could be a rocket. Could be like a weak rocket, a mid rocket, and a very powerful rocket. That could be the force. What's going to happen to the acceleration of the first one? A lot of acceleration or a little? Little. The lots of force is going to give me lots of acceleration. And the mid force is going to give me mid acceleration. And I think nobody's going to argue about that. You know? And if I was going to graph it, somebody say, oh, okay, well, I guess that means that if I have axes like this, the more force I give to something, the more acceleration it'll have, or the more acceleration I observe, I might conclude that there must have been more force causing it. One way or the other, one goes up, the other one goes up. And so what Newton says is force, and here's the symbol we use today, is proportional to, that's not a fish, it's actually the Greek letter alpha. And the way we read that symbol is proportional to. And I would expect that a lot of the math teachers would have used it in math class, but that symbol, that alpha, reads proportional to. Force is proportional to acceleration. More force, more acceleration. Makes sense, right? Stronger rocket, more acceleration. Push the gas down on the car harder, car accelerates more. Makes sense. Take that away. That's the first proportionality. And that's what we talk about right here. I could sketch it out. A, F, F, F. More force, more A. Now, the acceleration of an object is inversely proportional to the mass of an object being pushed. I'm going to grab another Post-it note. You can write it in the white space here or at the top of the page, but I'm going to use a Post-it note just so that it records nicely for you. And again, I want to draw a series of cartoons, and the series of cartoons would go like this. Only this time, I start off with that small mass, and instead of changing the force, in my thought experiment, I would say, well, what would happen if I have bigger mass? Bigger mass. And last time what I said was I was going to increase the force, but keep the mass constant. Maybe I didn't explicitly say it, but hey, look, each of these things were the same size, so we were keeping the mass constant. Okay? This time, though, I'm starting off with a small mass. Then I've got a bigger mass. Then I've got an even bigger mass. And what I'd really like to do this time is instead of keeping the mass constant, I'd like to keep the force constant. It seems to me that if I keep the force constant, here, F, F. Keep my arrows the same size, keeping my font the same size. F, F, F. Let's think about what would happen if I pushed a skateboard, if I tried to push, I don't know, a car, yeah, if I tried to push a train. right? I'm scaling up the mass, right? And it doesn't have to be me doing the pushing. It could be a standardized rocket engine trying to push a skateboard. Imagine that. A car mounted on the top of the car, mounted on the top of a train. This is very like cartoon, Warner Brothers, Bugs Bunny type stuff, right? But if I did that, look, mid-size force, tiny mass, this is our skateboard. What's going to be true about the acceleration? Huge, huge acceleration. Mid-size acceleration. What's going to be true about the last one? Tiny, tiny acceleration, right? And so I do these letters just like to, because we know this. We know, but size of letters makes sense. What we actually say is, and this is a hard one to realize that it's not actually linear, is that if I think about the acceleration, as the mass increases, what's going to happen to the acceleration? It's going to decrease, and it's going to look something like this. It's going to be some sort of an inverse proportionality. It's going to drop off for us. It actually turns out it's not linear, but it does drop off like this, okay? And so qualitatively, that kind of makes sense. And Newton says, okay, well, I could sketch it out as maybe you did. Same force, same force, same force. Big acceleration, mid acceleration, tiny acceleration. Okay, but the idea is that for this one, more force, more acceleration. For this one, more mass, less acceleration. Drops off. And if we bring these two ideas together, what Newton actually says is that we can write it as an equality. And we can say F is equal to ma. Now F equals ma doesn't actually sound exactly like these two things. If I really wanted to sound like these two things, I'd take this equation and I'd rearrange it a little bit. I could say, okay, well, for the first one, what I'm thinking about is the fact that, all right, look, if F increases, then acceleration increases. That makes sense. For the second one, I'm actually thinking about it more like this. I'm saying, okay, well, isolate the acceleration. Acceleration is equal to F over m. You see that way of rearranging that equation matches up with that proportionality. But either way, it's F equals ma. Okay? Now, most people are going to write it in the format that's in the rectangular box there, mostly because it fits better on a typewriter, but also because it is easier to say F equals ma rather than acceleration equals force divided by mass. Just easier. But it does acknowledge both of those proportionalities. I want to think about how we can calculate things. Now, just as a quick aside, I want to acknowledge that Newton himself didn't think of his own second law that way. Newton actually thought about it this way. And I'll just do this one quick little rabbit hole and then I'll move on. You know how acceleration is equal to v2 minus v1 divided by delta t? Here's my acceleration, right? What Newton said was, if I take that equation and I take that equation and I sub the one at the top into the one that's yellow here, then I could write F is equal to mass times v2 minus v1 over delta t. Distribute the mass through the binomial, you get mass times v2 minus mass times v1 divided by delta t. And when I look at this, I'm like, oh, so then there's like this mass volume thing, and there's a final mass volume thing and an initial mass volume thing divided by time. And Newton himself thought about his own second law as the rate of change of what he called momentum. Mass times velocity is momentum. He actually called it impetus, but momentum. Impetus is Latin, but we call it momentum today. But the rate of change of momentum is how he talked about his own second law. Today, though, we don't talk about it that way. Grade 12, maybe we'll come back to it. We'll talk about momentum some more. For now, I'm going to slide that off the screen because that's not the way we'll talk about it. I just want to say, hey, he liked this idea of what happens with mass and velocity, and that actually relates nicely to inertia, right? So there's a crossover. You can tell how the man thinks. We're going to talk about it as mass times acceleration. Anyway, these two proportionalities come together, and we can take a look at this object. And we got this object here. This is an object with a free body diagram. We know its mass is 5 kilogram. It looks like there's only one force acting on it. The first thing that we should always do with a situation like this is draw a reference frame. And so my reference frame, I don't have any context for this. So I'm just going to say up is positive. Maybe to the right is positive. Down. I don't know what to call all this stuff because I have zero story being told to me. Let's make left be negative. So I'm coming up with a reference frame just because I need something to hang my hat on. And it says find the acceleration. Well, if I know mass and I know the only force that's present here, I can say, well, force is equal to mass times acceleration. Now, I will take this opportunity to say that a lot of times people will write that force as the net, F net. F net, the net force. The sum of all the forces is equal to mass times acceleration. So F net is equal to mass times acceleration. Well, that means that if I want to get the acceleration is equal to F net over mass. And I'm putting that net in there right now. I'm going to ask you to as well, so that we really emphasize, because we're going to need it moving forward. And I can sub in my values. Well, it looks like F net is just F1, so 10.0 newtons. And it looks like it's to the right, so it's positive. And the mass is 5.0 kilograms. And I say, okay, well, if I do that math, 10 divided by 5, we can do that in our heads. Somebody shout out the answer. What is it? 2. Not just 2, but 2.0. Sig figs. 2.0. And then the units, well, usually we think acceleration meters per second squared. Let's just acknowledge what's going on with the units here. It's positive, so it's to the right. But I want to do a quick little unit conversation off to the side. I'll do it in color. But if F equals ma, Newton's second law, I already kind of just used it without saying it. What are the units for force? The Newton. The Newton is the unit of force. I'll put brackets around it just because we're doing a unit conversation here. What are the units for mass? Kilograms. What are the units for acceleration? Meters per second squared. So it turns out that if I look under the hood to see what's inside of a Newton, a lot of the times what we do is we'll have these units that are derived units. Units that come from a formula. And we shorten them up. And oftentimes when we shorten them up, we bury the units along with the grave of a dead person. In this case, the dead person's Newton. So buried inside of Newton is kilogram meters per second squared. So anytime you see a Newton, you need to know that a Newton is just a short form way of saying kilogram meters per second squared. Is that clear? Okay? So anytime you see a Tesla as a unit, anytime you see a joule as a unit, anytime you see a watt as a unit, these are all dead people. And buried alongside that unit or inside that unit is a composite unit, a derived unit, okay? So just to make sure that's clear, anytime you see a dead person's last name, units are inside of it. Anytime you see a dead person's last name as a unit, you always have to capitalize it. Notice that I'm using capital N for newtons. It's because it's a person's name, okay? Names get capitalizations. Meters and kilograms do not. That's not anybody's last name. Nobody died to make that unit, okay? Newton, that's the last name, all right? I'm not saying he died to make the unit. I'm saying, you know what I mean, right? Somebody, it's a person's name. All right, so let's take a look at this next one. I got a new free body diagram. Now, it's a bit of a drag, but yeah, I gotta have a reference frame. Up, down, right, left. Now I'm gonna make up and down be positive and negative, but as I look at my free body diagram, I think to myself, self, which force is winning this tug of war? Force 1 or force 2? 2. Strategically, I like to put in as many dominant positive signs as I can. So if I kind of look at this and I think, oh, left is going to win the tug of war, I'd like to make this easy on myself. Maybe I'll make left be positive this time. I like to play that little game. You don't have to. But I say still, I start off, F net is still equal to mass times acceleration. But it says again that I have to find the acceleration. All right, well, acceleration is going to rearrange to be F net over m. take the m down to the denominator, having divided both sides by m. I can sub in my values, and I think, nuts. F net isn't F1 or F2. Doesn't net mean the sum? Just like in business, it means the total of all your assets or your debts or whatever. So F net is going to be F1 plus F2. That's why the net's important. F1 plus F2 divided by mass. And you can write the A all the way down the equal signs. We've got to make all of our equal signs line up. But when I sub in my values, notice that F1 is negative 10 newtons, because it's to the right, and we declared that right was negative. Negative 10 newtons, I'm writing my units, plus F2, 12 newtons, positive 12 newtons if you like, divided by the mass, 5 kilograms. Somebody with a calculator, help me out. Maybe you can do it in your head. Negative 10 plus 12 divided by 5. Yep.
0.40
Yeah, you got it. 0.40 meters per second squared. And in terms of the meters per second squared, let's just remember that buried inside of a Newton is a kilogram meter per second squared. And if I'm going to divide that by a meter per second squared, or sorry, divide that by a kilogram rather, the kilograms are going to cancel out, and it's going to leave behind the meter per second squared, okay? So just to make sure that we're really clear about why it ends up being meters per second squared, but I'll go with that. Now the fact that that acceleration is positive means that I should put what square bracket on there? Left or right? Yep. Left. Okay, so based on my reference frame. Now there's no story here, so I'm not going to do a therefore statement. Okay? Not a story this time, so I'm just going to keep on going. I want to take a look at this one. And I'm trying to go through all these different permutations of what we could do with these things. I've got an object that has two forces on it, only this time it says the velocity is constant. If the velocity is constant, what does that tell you about the acceleration? Yeah? 0, yeah. So I'm reading between the lines here. If the velocity is constant, that means, in words, that acceleration is 0 meters per second squared. And that's good to know. But we have to, it's a reminder, we have to read words, not just about pictures and numbers. But it says, find the F2. Okay, so I got to find F2. It seems to me that we could still start off with F net equals mass times acceleration. However, I could expand that F net to be F1 plus F2 equals mass times acceleration. Hey, why don't we do this? Why don't we make a reference frame? And just to show that it doesn't really matter which one's positive and which one's negative, let's make up and down positive, negative. But let's make to this time, let's make to the right. Let's go back to our old ways. Right positive and left negative. See how this goes. Do I know the F1 value? Yes, I do. Do I know the F2 value? No, I do not. Do I know the mass? Yes, I do. Do I know the acceleration? Yes, I do. So I'm trying to find F2. This is the one that I'm trying to get to. If I'm an algebra person, I could get the F2 all by itself right now. I could say F2 is equal to mass times acceleration minus F1. However, notice I just took the F1 over to the other side. Isn't the acceleration equal to 0? So if the acceleration is equal to 0, either at this line or at this line, I could recognize that that's going to be 0. Okay? And I know F1 is 10 newtons, so the minus is a part of the formula. Okay. 10.0 newtons is the value of F1, and what we're saying is F2 must be equal to negative 10 newtons. Or we could say F2 is equal to 10.0 newtons, negative was left. Okay, so we've got a nice systematic way to do this. And I know that there's some people that like to do things by inspiration rather than following algorithms. And they might say, well, right at the beginning, I can tell by logic that the acceleration is 0, so then this has to be a stalemate tug of war, right? It's a tie if this was a tug of war. I can tell that right from the beginning. And that's great for you. but you still need to be able to show your work, okay? You need to be able to show how your inspiration works out on paper, okay? And I love that you can do that if you can, but we got to be able to be systematic about it. All right, let's take a look at this next one. And then finally, with this fourth one, we're breaking out of one-dimensional thinking and being two-dimensional thinkers. And as soon as I look at this, I think, oh, by golly, XY components, SOHCAHTOA, Pythagorean theorem, it hasn't left me. I still got to know this stuff, right? Like, this is something that isn't going away. If it was a struggle from a previous unit, we're still with this thing. Anyway, the question is, find the acceleration. Well, the question starts out the same when I write it down. I say F net is equal to mass times acceleration. And I can still say acceleration is equal to F net divided by mass. But it's at this stage where I think, like, well, what's F net? Is it going to be 10 plus 12 equals 22? What do I have to do? Pythagorean theorem, right? And that's okay. We're borrowing previous skills here, right? So we're saying, well, F net is going to be F1 plus F2, which means that the sum of those two is the F net. I add them tip to tail to get my F net, because that's what it means to add up vectors in 2 dimensions. And it would go off at an angle. Oh, shoot. That means that it's not just left, right, up, down. It's like some sort of a directional notation. You know what? Because we haven't dealt that well with left, right, up, down with directions, why don't we switch? Why don't we just, because again, there is no story. Just for argument's sake, let's be north. Let's let north be this direction, south be this direction, east and west. For this one, okay. And we can let north be positive and east be positive, south and west be negative, because it looks like it's kind of going like north and east. So strategically, that's going to be okay for us. But we're going to have to find the magnitude of F net and the theta value. So I say, okay, well, F net is equal to F1 squared plus F2 squared. Are you guys okay with me just square rooting the right-hand side? Just to avoid an extra line. We'll square root that. And as I sub in my values, I got 10 newtons squared plus 12 newtons squared, all square rooted. I need someone with a calculator. What's F net equal to? You got it already? Yeah.
15.6205.
15. Can I get, does anybody want to second that motion? Yeah? 15.62, not that I don't trust you. 15.6205. Make sure that we got it. Okay, so we've got a magnitude. We still have to have a direction. Do you like sine, cos, or tan the best for this one, for the theta value? Tan. Look at this. We got the opposite and the adjacent here. So we say, all right, well, tan theta equals F2 is the opposite. Remember, I'm not using op and adj. I'm using actual variables. F1 is the adjacent. So theta is equal to tan inverse of F2 was my 12 newtons. And if it makes you feel more comfortable, write that there so that you can see that. 12 newtons divided by 10 newtons. So what angle does this thing accelerate off at? Or what angle does the net force go off at? I think it'll be like 50 point something. What is it?
Yeah, 50.1944.
50.1944 degrees. Now, for those people that are committed to this, because they're always checking out the answers in the textbook or whatever, or in the back of the workbook, you know that if theta is this value, then we could also have an angle here relative to the east that would be 90 minus that value. And so like just for argument's sake, we could say, hey, if you're really committed to the more acute angle, 90 minus 50.1944 degrees is equal to, I had it jotted down here, 39.805, I think. Degrees. So that's the more acute value. So both of those would be reasonable directions. It's just that one would be north 50.2 degrees east, and the other one would be east 39.8 degrees north. Okay, so, but let's come back to that in just a minute. I want to go over to the left-hand side again and say, okay, well, acceleration is equal to F net, well, we calculated that magnitude, is 15.6205 newtons divided by a mass, 5 kilograms. And so we get an acceleration magnitude. Somebody help me out. It's 3 point something or other. Yep. 124. Okay. Meters per second squared. It seems to me we only have 2 sig figs here, so we're going to have to round that off to approximately 3.1 meters per second squared. And in terms of the direction, either we write this as north 50 degrees east, or we write it as east 40, because 39.8 would round to 2 sig figs of 40. East 40 degrees north. Okay? Because we're only rounding to 2 significant figures, which feels unsatisfying because it feels like we should have more decimals in there or something. And if you really want to take the ambiguity out, you can put a line over top of those zeros just to show that they count for sig figs, okay? But 50 plus 40 does add up to 90.